So here we've got lambda, an eigenvalue of an n by n matrix A, and we want to show that this polynomial of lambda, lambda cubed minus 2 lambda plus 3, is an eigenvalue of a cubed minus 2a plus 3i. So something really important to note here is that the polynomial here, if we let p of x be x cubed minus 2x plus 3, then note that this is p of lambda. And this is actually P of A right here. Sort of where we have this little distinction on the, we need an I there so that we're not adding the number 3, but 3 times an n by n matrix. There's a very specific relationship between the two. And that relationship is just going to sort of fall in place when we multiply by the eigenvector. So if lambda is an eigenvalue of A, we do know what that means, that there's a non-zero x vector with ax equals lambda x, right? So anytime you're told that something's an eigenvalue, this is how we want to translate that, because this is going to be usable. This gives us a math equation that we can manipulate. And so our goal is to show this eigenvalue here. And so basically what we're going to do is just assume this x is going to have something to do with that construction, because we see all those a's and we know how x reacts with a. So we're going to just throw x up against that and see what happens. So if I do a cubed minus 2a, so this is my matrix, my new n by n matrix. So what I can do here is expand and simplify this thing. So a cubed x, I'm going to just kind of work that out on the side. So this is ax, right? That's what a cube is. And the ax, each ax is going to turn into a lambda x. And the lambda, I can just sort of pull to the front and keep doing it to get a, so I've got my lambda, a lambda x. And then I can just do this one more time on the ax. And we get that lambda cubed. So like no matter how many a's I throw against x, they're all just going to turn into lambdas. And so when I clean this thing up, it's actually lambda cubed times x minus 2 lambda x plus 3, and that's just x, right? Ix is just x. And you can see now we can right factor the x from all of this. Well, it actually doesn't matter if it's right or left because it's constant coefficients here, but we can factor it. And so, yeah, we get this relationship. This is exactly that P of lambda that I was talking about above there. And I know that when I throw this x against this combined matrix, I get this multiple of x. And so by the definition of eigenvalues and eigenvectors, x is also the eigenvector for this mashup of A. And it's with the corresponding eigenvalue of lambda cubed minus 2 lambda plus 3. Of a cubed minus 2a plus 3i. And specifically, again, x is a non-zero vector there, so it's not like that combination of lambdas is gonna wipe out with the x or anything. So it's still gonna be consistent with the definition of what it means to be an eigenvalue. And this is our conclusion. And so we're done.